Thank you. I will share my screen first. Can you see my slides?
Yes, it is coming. Yeah. Please go to the full screen mode.
Is it here?
Yes, your slides are visible. Please go ahead.
Thank you. Yeah, first of all, I wish to thank the organizers for the invitation to be at this very interesting conference, which is in celebration of Professor Ashutosh Sharma's 65th birthday. And I'm sorry that I couldn't be there with you in person, but I'm really thankful and honored to be available online. So let me start by wishing a very happy birthday, Ashutosh. Wish you decades more of exciting even healthy life, with a great time with family and lots of friends that you have had. Professor Sharma, in addition to your great presence in the technology, research, innovation, and policy, we often think of you for your creative arts, particularly paintings. In fact, JNCASR has been a beneficiary of some of your paintings on its walls, and also your witty and deep philosophical discourses, which we often remember and benefit from. We look forward to many more years with you of very interesting interactions to go forward. Let me just talk about very briefly some ideas I have on the work that I was involved in, which relates to sustainability and in particular technology and policy. And this is going to revolve around energy transition, which is a very important sort of evolution in technologies and scientific landscape that is happening today. It very intimately links with the problem of environment, specifically global warming, and that leads to a concept of carbon recycling and working with carbon dioxide, and also relates to hydrogen as a chemical fuel, which is very important to store renewable energy as well as using it in many other chemical reactions. And of course, for all of these technological challenges, very important is the science of materials, and in particular catalysts, as you will see in the next few slides. So catalysts are of course created in chemical engineers like Ashutosh and many other people. More particularly, they cover 80 to 90% of chemical processes which are all around us from day-to-day life to, of course, industrial operations as well. They contribute to about 30 to 40% of global GDP, and consumption of a catalyst with the worth of $1 often produces products which are worth more than $300. And that's why they're very important materials. And accelerated design of catalysts is very interesting in terms of basic science as well. It involves theory, simulations, machine learning, and of course, without experimentation, it is always incomplete. So, let me talk to you what I mean by energy transition. So, if you look at the projection that various governments in the globe have been making, presently the energy sources are green sources, include solar and wind energy, and also another form of energy, nuclear energy. And you will see that present percentage is just 25%. And 2070, this is well after the Vikasik by the way, this percentage is going to grow quite a lot. Solar and wind energy is going to grow to 45%, and nuclear energy may double in terms of percentage of production. But at the same time, I want to draw your attention to, at present, we have coal, oil and gas as the main sources of energy, which about 81% of the energy come from these sources. And this is going to reduce as a result of this green revolution to 22% of the total energy production and consumption. And which is not zero. And at the same time, the total energy needs of the globe is going to go from 600 exajoules to 975 exajoules. So if you look at the percentage, coal, oil and gas are going to continue to be relevant sources of energy, although with lesser and lesser importance for the next 25 years. And how do you go from this present 2070? It's a period of 35 years. And what 45 years, and it's not easy. Yeah? And I think this is called energy transition to go from present to this target, and that requires development of technologies at different time scales. And this transition, how to plan is what I'm going to tell you. And one particular aspect which is very important in planning this energy transition is hydrocarbons. Hydrocarbons, all of us know, are already used extensively as sources of energy, and they are very unique in the sense of storage as well as conversion of energy. You will see this chart which is taken from Shell Oil Company, and on the y-axis is basically the duration for which we can store energy, and on the x-axis is the energy amount of energy that we need to store. And hydrocarbons, which is this blue ellipse that you see, really stands all the details as opposed to other forms of energy storage, like batteries or thermal energy storage. These are surface-based materials energy storage or pumped hydroelectric storage, hydrogen. You will see they all are in a very narrow sort of region in the space of period and amount of energy storage. Yeah, so hydrocarbons are not something you can get away with very easily, and more importantly, they are also very important to the energy transition that I'm talking about, because we will not overnight change our energy from solar to fossil fuel solar. So there is something called green hydrocarbons, and these basically are recycled materials like plastic, polymers, all of which contain carbon, and basically you recycle them to generate fuels. Second is biomass feedstock, but this unfortunately is not scalable because you need 55,000 kilometers square of land to go to this biomass to be able to generate meaningful energy, and it's just not really practical. On the other hand, the third one which I will focus on is carbon dioxide capture, utilization, and storage. I feel is very relevant to this energy transition, and in this case you can reduce carbon dioxide to methane, methanol, or long-term which are like used in the aviation fuel using Fischer-Tropsch break-off reactions. Okay, so the concept here is you use renewable energy, which could be solar energy, along with combination of water and carbon dioxide to generate hydrocarbon fuel. And when you burn this hydrocarbon fuel, you will recover CO2 back, and that CO2 again can be used in the same reactor. That's what we mean by carbon recycling. And in this case, you can also replace this renewable energy in water with hydrogen. And hydrogen is basically the reducing agent to reduce carbon dioxide to something like methanol. And these reactions, of course, are facilitated by our appropriate catalyst, and that's where very interesting material science comes in, not only chemistry, physics, but also engineering to sort of develop reactors which can scale up this operation. Generation of hydrogen is another sort of technology that needs to be looked at, and solar energy to split water is also an important way scheme of generating hydrogen, and this is clean hydrogen. So in some sense, you can look at this technology, and we are also using the catalyst and build interesting materials. So this carbon recycling technology you can view as storage of renewable energy, as it's coming in here. It can also be looked at storage of hydrogen, which is another technological problem, and you can store it in the form of hydrocarbons or ammonia, and basically this is a very usable and portable fuel which can be readily used, methanol can be readily used in automobiles by very little modifications of the type tubes that are used. Okay, so this is the concept of carbon recycling and green hydrocarbons, and this is going to be quite important in the next 30 years when we make this transition from fossil fuels to completely renewable energy. And this is when I was involved in a startup company which was incubated at JNCASR. It's called Breed of Life Sciences Private Limited. This was a company where my role was to use basic science, in particular first principle basic quantum calculations, as helping design this. And this basically involves studying interaction of carbon dioxide and other intermediates like material and hydrogen with the surface of the catalyst, and look at basically the rates of reaction, the state, in reducing carbon dioxide, which is quite a challenging process because it transfer of 6 years. Okay, so this was a role of basic science. Then the team that we worked with, the co-founders, he's an engineer, Sebastian is a chemist, and myself a physics expertise. So Sebastian is of course continuing along with Rashid with this company in scaling up these operations, scaling up the production of catalysts and also conversion of CO2, and they are now very successful in producing 1,000 kilograms of CO2 per day, and the company is moving ahead under their leadership. This is of course possible due to a lot of teamwork, and Shomo, who was the key student of Sebastian, so made it possible, is now at IIT Kanpur, which is you are. So I'm really happy that this journey is going well. I will stop now by pointing out that many of us spoke about the GDP percentage of GDP and many other factors that government needs to improvise and help in facilitating translation of India's basic science to technologies. But from my experience, from what we can do on our own is basically we need to work together a lot more and not worry about individual gains. Second is we need to respect each type of work, however tedious and implementary it may be. Thirdly, we need to respect each little contribution of individuals around you so that it's finally recognized as a teamwork. Third, fourth, we need to take risk, high risk in choosing hard problems, and that's where we also are finally falling short. We also need to work much harder. I think we can't represent what we have and what we have achieved so far. So I do think government is making some policies and provisions to set up startup companies, but a lot more needs to be done. But these are my sort of wish list items on the wish list which scientists can do and achieve bigger things. So I take this opportunity to thank the organizers once again, and particularly Professor Sharma for being creating a forum like this that we can express all these ideas. Thank you very much.